Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
a riddle. If chemistry is a science in search of facts, why is imagination so important? The answer is wrapped in mysteries. Why are there enormous volcanoes of liquid sulfur on this distant planet? How do drugs work inside our bodies? And what explains the behavior of gases at different pressures? Chemists must probe events which cannot be observed directly. So imagination is the first step towards modeling the unseen.
I'm in one of my absolutely favorite places, the East Wing of the National Gallery in Washington. Let's take a look at some sculptures. Here is this marvelous sculpture by Alberto Giacometti, a seated woman, less elongated than his usual representations. You know, no doubt Giacometti used a clay model in constructing this bronze figure. And in another sense of the word model, this sculpture, all art, gives us a representation of the essence of some expression, of an emotion, of some response to a piece of the natural world around. The artist is trying to understand that world. Chemists also want to understand the world that we live in. And in order to do that, we have to form hypotheses and models. The models that we use are different from those that artists have. For instance, different from this beautiful sculpture by Isamu Noguchi. Chemists are often trying to observe things that we cannot see or touch directly.
Some things are too complex to study directly. A gas consists of billions of tiny particles. There are too many of them to observe all at once. So models are used to predict their behavior. Some processes happen too slowly. The geochemical events that produce this coal took place over millions of years. Some things are too far away to study firsthand. The chemistry on these outer planets can only be guessed through long-range and indirect observations. Even when we can observe events close up, we may still need models to understand the chemistry that produced them. From the chemistry of the largest bodies in our universe to the behavior of particles so small they are invisible, chemists use models to imagine, then test explanations. They need models because these events are like black boxes that can't be opened. How do scientists make models to reveal such inner mysteries? To unlock these secrets, series demonstrator Don Showalter went to a class of 6th graders.
We're here to solve a problem for you today. Many times in chemistry, what we are studying, we really can't see very well. In fact, we might not even be able to see it at all. So what we want to do, a little bit of an experiment with you today, and the experiment involves these two boxes. What we want to do is find out what's inside these boxes. All right, the box is locked so that we can't see inside the box. Now, what we want you to do is form in your mind a model. You know what a model is? Yes. What is a model? A model, sort of the idea, not a model like a model airplane, but maybe a model of a mental picture, huh? What could you do to be able to tell what's inside the box? How about if I passed it around? And now what I want you to do is to form a mental picture in your mind of what's inside that box. What do you notice about the two boxes in comparison?
One's heavy,
All right, one's heavy,
yeah.
One is light. All right, what else? What about?
One makes sound and one doesn't.
Good. What's that? Real loud.
One makes sound and one doesn't.
You betcha. One makes sound and one doesn't. Have you got a mental picture yet?
So
What's inside? What's inside the light one?
I don't know. It's neither big or else there's nothing in there.
Anyone else want to?
I think there's nothing because when you shake it, you don't hear anything, and it's light.
So you're using your ears, huh?
I think that there's like sponge or something soft in the box, because when you shake it, you don't hear anything, but the box feels heavier than if it were empty.
Okay. All right. Now I want you to hold on to that idea for a minute. All right. Now we want to hear about the heavy box over here. Here's the heavy people over here, huh? All right. Now.
I think there's chains in the box because when you shake it, you hear like chains going against the box, and it's heavy.
You hear what kind of a sound?
It's like clanking.
Like a rattling or clanking sort of sound in there, huh? And what else about the box?
It's real heavy.
It's heavy. It's heavy. So there's something in there that is dense. You know what that word means? Dense? Okay. Anyone else want to give us an idea about the heavy box?
There's just any kind of metal in there because the noise it makes.
Any way we can look inside things without actually opening them up?
We could x-ray the box to check what's in there.
All right. We've done that. You want to see them?
Heavy one.
That's the heavy one. What do you see in there?
Nuts.
Let me bring it over. All right. Boy, we were close, weren't we?
Yes.
You were right on. You were thinking that it had all that metal in there, and certainly the x-ray showed that up. So we could study that box without even opening it up. Okay. What do you see in here?
Nothing.
All right, so we say nothing's in that box, huh?
Right.
All right, everybody agree?
Yeah.
All right, everybody in agreement? Hold their hand up. All right, let's open these boxes up and see what's inside there, huh? All right, now this one, do you feel confident that this has nuts and bolts in it?
Yeah.
You're right on. You're right on. Look what's inside that box.
Nuts and bolts.
Nuts and bolts, huh? All righty. How about this box? What do we say?
Nothing.
Nothing inside there.
Possibility.
Possibility of having nothing inside. Here we go.
There's nothing in there.
All right. Cotton balls.
The steps a scientist follows to develop a model are along the same path traced by the students. First, scientists make general observations about a situation and closely observe the behavior of the system being studied. Then, relating these observations to their past experience, scientists try to imagine what model could explain their observations. Like the students, they build a model based on their past experience and their ongoing observations. Next, scientists must test their model. The students tested their models by examining X-rays of the two boxes. These tests are designed to confirm or disprove the model. One procedure, the X-ray test, supported a model that was false. When the box that looked empty was opened, it contained cotton balls. So scientists test their models using many different procedures. How does this method work in the real world? Let's start with a model of something on a very large scale. For centuries, scientists have been studying this kind of black box, our solar system. Until recently, these observations were limited to what could be seen through telescopes. We have had to rely heavily on models to explain the chemistry of these enormous bodies. One of these models concerned Io, the first moon of Jupiter. Dr. Torrance Johnson is director of the Voyager project.
Before we got spacecraft out to the Jovian system, basically what we knew about Io was how big it was, how much it weighed, and how bright it was to first order. How big it was and how much it weighed made it look just like the Earth's moon. So you started all of our modeling assumptions in the early days before Voyager started with the idea that Io was going to be basically like the moon. There was one problem. It was about 10 times brighter than the moon in terms of its surface reflectance.
Why was Io so bright? One model proposed that unlike our moon, Io had once been covered with great amounts of water. Volcanic activity had caused the water to evaporate, leaving behind a bright layer of salt deposits.
But because it was the same size as the moon, we thought that all of this heating activity had occurred 3 to 4 billion years in the past, just as the moon's had. So we thought it was dead. Our model was of a dead lunar interior with a salty outside, probably blasted full of craters by meteorites.
In 1977, the first Voyager probe was launched to gather observations on Jupiter and Io from close range. Scientists waited for 18 months as Voyager made its lonely pilgrimage. The wait was worth it.
What Voyager found, of course, was fantastically exciting. It found a body that's more volcanically active than any object we've ever seen in the solar system. The surface is covered with huge volcanic features, large collapse pits, calderas, volcanic flows, and most exciting of all, we caught several active volcanic eruptions in the process of going on with Voyager 1, throwing plumes of debris up 100 to 300 kilometers above the surface.
What could be the source of the energy for these volcanoes? Investigators proposed the following model. Io hangs in space between Jupiter at one end and Europa at the other. The gravitational force from each body tugs on Io, causing it to flex and heat up as represented here in exaggerated form. So in this model, gravitational energy generates the heat for the volcanism. But there was still something strange about the chemistry of these volcanoes. They weren't volcanic eruptions like the ones here on Earth with lava exploding or flowing out of the ground. Instead, they resulted from the same conditions that produced geysers, such as the ones in Yellowstone Park.
But they weren't water. We knew there wasn't any water now on Io. We have good spectroscopic evidence of that. So they proposed that the working fluid in this model was liquid sulfur or liquid sulfur dioxide, which can exist in the liquid state at fairly shallow depths below Io's crust.
But this raised another enigma. How did sulfur compounds instead of silicate rocks come to be the dominant lava on Io's surface? A new model arose. It proposed that long ago silicate rocks sank to the interior of Io. Water evaporated from the surface. Sulfur compounds were the lightest materials not to boil away. They ended up as the dominant lava. Is this the final model of Io's sulfur plumes?
But when you build a model like this, you shouldn't get to thinking that the model represents reality. It will always change. In fact, we're not doing our job right if it doesn't change. It'll always evolve as we get more information and revise our methods of observation based on the model.
The chemical processes on Io are vast in scale, and Io is very far away. A lot of chemistry involves an intellectual excursion in another direction, to the very small. Take, for instance, a gas. We can measure its volume, its temperature, its pressure, but what is really happening inside a gas?
In order to understand, predict, and control what is happening inside a gas, we use a model called the kinetic particle model of gases. It assumes that a gas consists of large numbers of extremely small particles. There are billions of these particles in one breath of air. Let's make some observations and see how this model explains them.
This apparatus that we have here will allow us to measure the pressure of a gas. Now, what we want to study now in our model here is several different variables: pressure, volume, and the amount of gas. One thing we're not going to vary is the temperature. We're going to hold that constant. The temperature of the room now will remain the same. Okay, let's do an experiment. What I want to do is add an amount of gas to this already trapped volume of gas in here. As I do, of course, you know that's going to increase the pressure. Right? I'm going to add some helium. Look at the pressure. I'm doubling the pressure. Once it's up there, I'm going to shut that off. Now Now what I have done is double the pressure of the gas. Now what do you think that means in terms of the amount of gas added? I bet you said it doubled the amount of gas, huh? That's the intuitive guess. And you're right. If we double the amount of gas, we double the pressure. Now we want our model to be able to explain that.
This is a representation of the container we used in our experiment with a vast number of gas particles already in it. The particles are moving chaotically in all directions and colliding with the walls of the container. For the purposes of our model, suppose that we could make the gas particles enormously larger and see them in slow motion. And to make things even clearer, we'll focus in on the behavior of just a few particles. As these particles collide with the walls of the container, the many tiny collisions exert a force on the walls. The force exerted on each unit of area of wall is the pressure of the gas, shown here on this gauge. What would happen if we double the number of the particles in the container? There are now twice as many collisions per second against the wall. What does this do to the pressure of the gas? It will double it, because the number of collisions in a given unit area is directly related to the pressure of the gas. The more collisions in a given unit of area, the higher the pressure.
Let's do a second experiment now. This time we're going to vary the volume and the pressure. Again, leaving temperature constant. What I'm going to do is release the piston and see if we can come up to this mark here, which refers to double of the volume. All right, so we release the piston. It comes up to double the volume. And look what happened to the pressure. The pressure now is half of what it was. It was on 2. Now it's back down to just a little bit below 1. It's down to about what it was originally. And so we have doubled the volume, and in the process, the pressure was cut in half. That's another observation that we've had. So we've done 2 experiments now involving the amount of gas and the pressure. In the second experiment now, we looked at the volume that the gas takes up, the volume of the container, and the pressure of the gas. Let's see how our model can explain these observations.
What happens to the pressure if the volume of the container is doubled, but the amount of gas particles is kept the same? As the volume of the container increases, the gas particles have more room to bounce around. They are now striking the wall only half as often as before. The pressure also drops back to half of what it was at the smaller volume of our gas. The kinetic particle model applies to any gas under standard conditions. However, in the real world, there are many different types of gases, and the particles of one gas are different from the particles of other gases. Yet, even though they are different, all groups of gas particles obey the general rules laid out in the kinetic particle model. This is true regardless of the type of gas particle. The kinetic particle model deals with the average behavior of large numbers of gas particles. It doesn't deal with the shape of single gas particles. But in other areas of chemistry, models of the actual shapes of single particles are very important. What you are looking at now is a model of a drug compound used to treat ulcers. These models have opened the door to an unseen world inside our bodies, a world where drug particles interact with cells on a submicroscopic, invisible level. They have led to remarkable discoveries in the fields of biochemistry and drug research. Dr. David Pensack and a team at DuPont are one of several groups creating computer models of particle structure. How are these models used in drug research?
Computers are very nice tools to help us better understand how nature puts her building blocks together to create the substances which we encounter in our daily life. What you're looking at now is a computer graphics picture of DNA, the thread of life. What we're trying to understand in any kind of a model is exactly what's going on at the level whereby nature is doing whatever it is happening. We cannot get down small enough physically to see that. So what we have to do is try to simulate this. The problem is that these particles are so small that by and large chemists have never really had the chance to create a mental picture of what they're like. So what we have to do is develop models to enable them to think about things that are too small for them to actually look at.
The key and lock model is an example. Picture a drug as a key. The cells in our bodies each contain many different kinds of locks. One of these locks, if opened, could result in a desired effect. But to open the lock, the key must be an exact fit. Computer models help researchers imagine the properly shaped particle.
The problem that we have is, yes, you have a key, and yes, it fits into a lock. Well, you have to worry about how does the lock and the key actually find each other, because they're both swimming around inside the body. There has to be some process of recognition whereby the key knows this is the lock that I want to interact with. And we call the process by which it approaches the lock the docking problem. We're trying to simulate it on the computer, very much the same as worrying about how a boat pulls up to a dock. It'll recognize where the appropriate slip is. But what makes this different than the boat docking problem is that we have a very oddly shaped slip, the hole in the lock, if you will, and we have to make sure we put just the right key in there. Because if the key that we put in doesn't fit, you don't get the desired activity at all. And if we have a key that can fit into multiple locks, you begin to have the side effects problem.
To create a new drug, researchers may need to synthesize hundreds of compounds and test each. It is expensive and time-consuming. Models streamline the process by identifying which particles have the highest potential for success. And because these models help researchers to see substances in new and different ways, they sometimes yield unexpected breakthroughs.
Let me tell you a little story that is near and dear to my heart. For a while we had two computer graphics systems side by side, and one of my people was working on developing a new class of weed killers. Another one was working on a class of molecules which are involved in treating of cancer. Certainly a high priority item. As luck would have it, they were both working in the room. They both got telephone calls at the same moment. They went back to their laboratories. When they came back, they inadvertently got on each other's terminal. And about 15 seconds later, the first one yelled out, "What are you working on my class of compounds for?" I said, "I'm not." And he said, "Yes, this is my compound over here." What came out of this was there was a similarity between the weed killer and the anti-cancer drug that had never been recognized before. Because the way we've been used to drawing these structures on a sheet of paper is in a stylized representation, which is really almost artificial. And you would have never seen that similarity. But when you displayed them exactly as nature was really dealing with them, there was a striking similarity. We wound up submitting some of our weed killers to the National Cancer Institute for screening, and it turns out they've got really significant anti-tumor activity. But who in their right mind would have ever thought of even taking a weed killer and dreaming that it would have any kind of activity in dealing with cancer?
To review, we use models to understand events and processes that we cannot see or touch directly. To develop a model, the scientist starts with observations. These observations are used to form a mental representation, a model, of the process being studied. Then the model must be tested. One important chemical model is the kinetic particle model of gases. It states that gases are composed of billions of submicroscopic particles in constant random motion. Models explain processes that vary from a very large scale to a very small scale, from the macro level to the micro level. They are used to understand the chemistry on the surface of distant planets, such as the massive sulfur volcanoes on Io. And they are also used to predict the behavior of infinitesimally small drug particles inside our bodies. For the chemist, models are a crucial tool for understanding the unseen.
It turns out that I am actually very much a model builder. I I want to tell you a little story about a piece of work. Actually, it was the work that won the Nobel Prize for me and for Kenichi Fukui of Japan in 1981, and that involved building models. There's an important class of organic reactions in which a chain is converted into a ring. Now, that looks like a rather simple process. It turns out to be actually a very important one in the chemistry of vitamin D. But when you look in detail at this process, all kinds of richnesses emerge. For instance, in the process of forming that ring, the two ends of the chain can rotate together like this, so that the red lines are on one side of the ring. Or, alternatively, they can rotate in another way, and now you see that the red lines are on opposite sides of the ring. Now, those are two different molecules, and the remarkable thing, and crucial for the chemistry of these molecules, is that one or the other of these rotations, not both, are followed depending on the number of carbon atoms in the chain. Fukui and I were able to construct a model using methods of physics to explain this preference. That model, within a very short period, was tested by the experiments of many people around the world. I wish I could tell you that every model that I have built has been as successful as this one. Some have been, and some haven't. Enough have been right to keep me going.
Funding for this program was provided by the Annenberg CPB project.